2019, and deep networks are already having quite a good performance in many different fields. And what they're good at, I'm going to refer to as the what task. So, for instance, you have this huge Inception V3 model trained on ImageNet, and you give it the image of a llama and ask it, what is this image? And you get the answer that this is a llama. So you have the what task, and your deep networks are pretty good at it. But you can imagine you can ask the second type of question, which is the why question. So you want to open the black box of the deep network and ask why the prediction was done the way it was. So there are two main ways to ask the why question. The first way is to ask what was about this input that was important. So which of the input features caused the model to think this is the image of a llama? So we call them the feature importance methods. Or in the specific case of image data, it's usually referred to as salience maps. Now, there is a second type of question you can ask, which is that what in the memory of the network caused it to think this is a llama? Or which of the training samples had the most effect for this specific prediction? So the why question of which one of the training samples had the most effect. We call them sample importance methods. So there have been several feature importance methods. We included 3 of them in our work, so simple gradient, deep lift, and iterated gradients. For sample importance methods, the literature is not that large, and we use the most recent method proposed called the influence functions. But before getting into the details of how we can attack the interpretation methods for deep networks, I thought it's maybe more important to see why even the robustness of interpretation matters. Why would we even care for our interpretations to be robust? So I'm going to give you a simple high-level example. Assume you have the setting of a court where you have an AI judge. So you have the defendant with its profile, so the defendant's sex, the defendant's crime, the background, their job, etc. And you have this black box AI judge to give you the verdict. And the verdict is guilty. So assuming any possible measure of legal actions, the defendant should be able to ask why I deserve to be guilty. And well, using the interpretation methods, you want to give the answer. So for a simple high-level answer here, your black box model says, well, the crime and background caused me to say that this defendant is guilty. Not their sex, not their race, not their job. Everything is fine and defendable. Assume you have a malicious defendant who wants to adversarially attack the AI judge. So they perturb, they change their profile in a way that it's not perceptible to human vision, but it changes the network or the black box AI judge's prediction. So it changes it to not guilty. But the biggest drawback with this kind of attack is that it's usually quite detectable by human observation. So for instance, in this case, the font has changed. So having a human judge overlooking the AI system, it can be detected that there was something malicious going on. The prediction itself has been attacked, while by any measure the defendant deserved to be guilty. But if you have a smarter defendant, what they can do is that instead of attacking the prediction, they do not change the prediction of the AI judge, but they try to change the interpretation. So the AI judge is still saying that the defendant is guilty, but instead of referring to the crime or the history of the defendant, it refers to sex, race, or job, which is not acceptable. So what happens is that the whole AI court system becomes debunked because the interpretation, the reasoning it's giving behind its actions is unacceptable. So having a robust interpretation is a matter of trust in AI. And the same example I mentioned here could be expanded to other fields, so you can assume specifically the medical field, that given two very similar inputs and a similar detection, you want to have similar interpretations. So how can we attack interpretation? How it is done? Going back to the old literature of adversarial label attack, so changing the prediction of the model, what is happening there is that we try to locally maximize the model's prediction to be different from the original or the ground truth. And it is usually done through maximizing the classification loss by having small perturbations. So you can use the very similar idea for interpretation, and how it works is that we try to maximize the measure of difference between original interpretation and the perturbed interpretation. So going back over this sentence, you have your original interpretation, so xt is your test input, n is your trained model, and I would be the interpretation. So no matter whether it is a feature importance interpretation or a sample importance interpretation, it is going to be a vector. So if it is a feature importance interpretation, it's going to be a vector over the size of input features. If it is a sample importance, it's going to be over your training samples. Then you have your perturbed input, so xt plus delta, and you're going to get a prediction and an interpretation for the perturbed input. Then we try to maximize the difference between the interpretation of these two. And as usual for the case of adversarial attack, we have our own constraints to satisfy. So first of all, the perturbation should be small, but the most important constraint here, in addition to all constraints, is that we don't want the prediction to change, because we just want to change the interpretation. So going back to this sentence, I said maximize a difference. So what can be our measure of difference between two interpretations? So these two are both importance vectors. If they are feature importance or sample importance, they are both vectors of importance. So one way to measure the difference between these two is going to be to see the rank correlation. So which features are important for the first one, and which features are important for the second one, and how does the ranking of features comparing these two vectors? Or you can say, we just care about the most important features, or the most important training samples, the top K most important, and we try to perturb the input such that we have the least intersection between these two. And for the specific case of saliency maps, so image data and feature importance interpretation, we can try to think of the difference as visual dissimilarity. So you have two saliency maps that look totally different. And using each of these measures, we can create a new attack against interpretation. So this is attacking the top K intersection directly. So you can see as we perform the iterations of the attack, the saliency map changes, so it goes from the tiger toward the stone. Or this is attacking the visual dissimilarity. So you can see in the beginning we're totally looking at the tiger, and as time goes by, as we do more iterations of attack, the interpretation starts making sense. So this is both of them together. And it works for all the three methods of feature importance that I mentioned. So simple gradient or sensitivity analysis, deep lift, and the famous method of integrated gradients. Going back to sample importance methods, we have the same behavior. So in the top row, you have an image of a sunflower. It is predicted correctly, and you can see the top three training images that are the most influential are shown. Now we perturb it a little bit, and as you can see, it's not detectable by human eye. So it's still predicted as a sunflower, even more confidently, but the most important training samples are totally changed. Now, talking about why this happens, the reason behind interpretation fragility. So look at the black dot, the dark black dot. Let's say that's our input sample. Now, as you can see, the green dot beneath it is the training sample that has the most importance for prediction, and the direction of the gradient can be assumed as the feature importance. So with a small perturbation, due to the nonlinear decision boundary of the deep network, you can see that we can perturb the black dot toward the gray dot. So not only the direction of gradient changes, in other words, the feature importance interpretation changes, but also we can see that the most influential training point for that classification task changes. Going back to the previous literature, so adversarial label attack, there, instead of perturbing the point to a different decision boundary, we perturb the point to the other side of the decision boundary. So that's the difference between these two methods of attack. So in general, fragility of interpretation is important. If it is fragile, it removes the whole trust in the system. Both methods of interpretability, so feature importance and sample importance, can be easily attacked. And thirdly, the reason behind fragility of interpretation is the model itself. So similar behind fragility of prediction. You have nonlinearity and you have high dimensionality. So thank you.